Yeah. So shall we get started? So what was the last topic we saw? So potential energy of a dipole when you place it in uniform electric field. So what is the value of it? P vector dot E vector, right? And we saw a problem also based on the concept, right? So as I told you, the last part of this, last topic of the first part of this chapter is electrostatics of conductors. Okay, this is a theory-based topic, but which is very important, right? So start writing it down. So first, write down the heading as electrostatics of conductors. 1 minute. Those who are online, you're able to hear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes. So what is the topic? Electrostatics of conductors. So generally when you say conductor, what comes to your mind? So when we say conductors, what comes to our mind? So generally when you talk about electric conductor, then that material will allow the charges to flow within it, right? But if you see the concept, right, it is not about electricity within a conductor, rather it is electrostatics of a conductor. What is the meaning of it? Think of the topic very clearly, observe the topic and then decide. Means what are we trying to say? Yes. So the question is, generally when you take a conductor, right, when you take a conductor, you connect it across the battery, then what will happen to the charges? Then what will happen? Charges will start flowing, right? But this is not what they're saying. You just take a conductor, instead of connecting it to an external battery, what will happen if you give charge to that material? Okay, that's what this topic is all about. So listen to this carefully. There are 6 properties that we need to discuss. One is, the first one, if you see, inside a conductor, okay, this is what they're saying. Inside a conductor, electrostatic field is 0. What is happening? If you take a conductor, inside, the electrostatic field is said to be 0. Please write down this point. This is a very, very important point. So this is a topic. It's inside a conductor, electrostatic field is 0. It is here. Okay. Now we need to give an explanation to it. What exactly are they trying to tell us? So what are they trying to tell us is the question. So if I have a conductor, can you give me an example of conductor? Metals, you take, let's say you have an aluminum sheet, okay. You have seen these wraps, right? Where they wrap food and give you. You take that kind of a thin sheet, which is an aluminum wrap. You take that aluminum wrap and make it like a sheet in the form of a rectangle and place it in the external electric field. Right? Now, what is going to happen to this? This is a question. So, if you place it in the external electric field, let's say E0. Okay. Now, what is present inside a conductor? By default, what can you find inside a conductor? What electrons? They are called free electrons. Why do we call them as free electrons? Because they have the ability to move around. Right? Generally, when you take a conductor, you have free electrons. Now, if I take this to be the direction of electric field, let's say I've applied uniform electric field, then which side is positive and which side is negative? 1 minute. So, left is positive. I'll draw it like this, E0. Remember, this E0 is getting pierced through the conductor also. Okay. So, left hand side is positive, right hand side is negative. Now, you guys told me that within a conductor, what is present? Free electrons are present. So, what will those free electrons tend to do when they are in the presence of electric field? They get attracted towards which charge? Positive charge. So, the free electrons inside the conductor, can I say they will come and get settled at the left end? Just give me a minute. So they will come and get settled at the left end of the conductor. Accepted. As a result of which, there is some deficiency created on the right hand side. So the positive charge is going to sit like this. So in between, it is hollow. Correct? Are you able to visualize it? So what is present inside? The negative charges are there. They have got drifted to the right. But the positive charge that is there on the right hand side, are they literally protons? That is because of deficiency of electrons. We are calling it as a virtual positive charge. If that is the case, then I can say that there is going to be an electric field generated inside the conductor. From where to where? From right to left, and this electric field, I'll call it as EIN, which I call it as induced electric field. What is it called as? Induced electric field. Okay. And remember, you have an external electric field already present inside because it has got pierced through the material. So E naught is already there due to the external source, and E is created due to the value of E naught. Now this process will be so quick inside a conductor in such a way that within no time you can say that E naught will be equal to En. Okay, this process inside a conductor will happen very fast, right? That E naught, that is the external electric field, will exactly be equal to induced electric field in terms of magnitude, but in terms of direction, they both are opposite to each other. So if I take the net electric field inside, can I write it as E naught minus E induced? Right? When E naught is equal to E induced, then E naught minus E induced will be how much? So this is the meaning of the statement that they're given. Okay, if I have to correct it, right, where they sold electrostatic field, right, you have to say net electrostatic field inside a conductor is 0. Okay, all these are happening under what condition? When the conductor is not conducting. Means when the conductor is not allowing the charges to flow, all these things are happening under static condition. That is why the topic is electrostatics of conductors. Okay, please make a note of it. It will vary accordingly. Inside also will vary.
Sir, but the electrons present within a conductor will be as a specified value, sir.
It has nothing to do with the value. There is an induced electric field. So the external one is able to create a certain amount of drift. That is the logic. Okay. So what they are trying to say is, irrespective of whatever the field that you're trying to give, if you take a conductor in a static condition, by default, it is always, by default, the net electrostatic field inside is always 0. That is the meaning. It has nothing to do with the magnitude of charge of electron or anything. Okay. So am I clear with this point? Shall I move on? Shall I proceed to the next topic? Yeah, tell me.
Sir, the net electric field in the outside will not affect the electric field that is within the conductor.
Which one? The electric field outside? Can you repeat?
Sir, like when there are two electric fields, won't it affect each other?
No. Just see, one is already present.
Yes.
There are not two electric fields. Listen, this external electric field is present. In the presence of external electric field, you are keeping this conductor. Okay. If you take this conductor by default and you leave it free, let's say this conductor is in the presence of gravitational field, nothing would have happened. The free electrons inside would have randomly moved in some direction. They will be moving like this. That is what actually happens. Okay, this is the reality. As soon as you place this in the presence of external electric field, so from the gravitational field, if you shift it to electrostatic field, what happens is the negative charge is going to get drifted and it will get located on the left end. You understood the logic why it is so, because when I say the external electric field is from left to right, by default my left hand side is positive and right hand side is negative, and we also know the fact that the electrons will start experiencing force in the direction opposite to the electric field. You're able to understand? Yes. So that is the reason why, since there is a gap here, right? So since there is a gap existing, I can say that right hand side is going to be positive, and you can say that there is a new field which is happening only within the conductor, which I call it as induced electric field. Clear?
Yes, sir.
Yeah. Shall we proceed? Listen. So what is the next topic, guys? If you see at the surface of the conductor, okay, have every point in mind because they are interrelated. Okay. If you look at the surface of the conductor, what are they trying to say? Electrostatic field must be, they are not saying could have been or something like this. They are saying it's a must condition. It must be perpendicular to the surface of the conductor at that point. Okay, please make a note of it. At the surface of a charged conductor, at the surface of a charged conductor, electrostatic field must be normal to the surface at every point. Electrostatic field must be normal to the surface at every point. So let's see how this works. Right. Okay. So if I take a conductor in this way, so what is the statement starting with? At the surface of a what conductor? Charge. What do you mean by charge? So when generally if you take a conductor, by default is it charged always? It is always neutral. When you say neutral, it has equal number of positive and negative charges, right? It is going to be neutral. But as soon as you charge means there is excess amount of charge present on the material, right? So I'll tell you in the next context, remember that this excess charge that you're trying to give will always sit on the surface of the conductor. Why is it happening? You will see it in the next point. The interior of a conductor can have no excess charge in the static situation. Okay. So as of now, accept the fact that all the excess charge you're going to give is going to sit on the surface of the conductor. Are you able to understand? So it is going to sit on the surface of the conductor. Now, if I take a tangent at a particular point, okay, to this tangent, let's say I am assuming that the electric field is not perpendicular. What am I assuming? I'm assuming that the electric field at a given point is not perpendicular and it is inclined, let's say, at an angle theta with respect to the point, with respect to the tangent at the given point. Then this electric field can be resolved into two components. What are the two components? E cos theta and E sin theta. Now, this E cos theta, since it is acting along the tangential surface, what effect will it create on that excess charge? When you place a charge in the direction of electric field, what will it tend to do? If I take a charge Q naught and place it in electric field, what will happen to that charge? It will experience force of what value? Q into E. Now, this E cos theta component, since it is tangential to the surface, to the charge already present on the surface, what can it do? It can make the charges move. Correct? So it can make these charges move in the sense, will those charges be static under static condition anymore as soon as they start moving? But what are we trying to discuss? So we are saying everything is being discussed under static condition. So when you're talking about electrostatics of conductor, we need to ensure that E cos theta is a component which is tangential to the surface is always 0. So if E cos theta has to be 0, electric field cannot be 0. Okay, then cos theta has to be 0. When cos theta is 0, how much is the value of theta? So this is the reason why it should always be perpendicular. So what is the logic you will write is, had the electric field not been perpendicular to the surface, then what would have happened? There would have been a tangential component which would have created force on the charges present. You're able to understand? Due to which what is violated? Static condition will be violated. Okay. So for the static condition to still stay strong, E cos theta should be 0 and cos theta should be 0 and theta should be pi by 2. That is 90 degrees. Is it clear, guys? So what are the logic you have written? Can someone repeat it? When the excess charge is going to sit on the surface of the conductor, if electric field was not perpendicular to the surface, then what would have happened? Tangential component of electric field would have generated force on the excess charge, which violates the condition of static, which violates the condition of electrostatics. Okay, see, it is exactly the same thing that is given here, but I tried to show you mathematically. Okay, next, the interior of a conductor can have no excess charge in the static condition. So, third point, the interior of a conductor can have no excess charge. Means if you give excess charge, where will it go and sit? If it is not sitting interior, where should it sit? Obviously on the exterior part, outside, right? So generally when you take a neutral conductor, it has equal amount of positive and negative charges. There is no concept of excess charge here, right? When you give that excess charge, then what should happen is it should go and sit on the surface. Let's see why. Okay. If I take, listen to this carefully. If I take a Gaussian surface just below the surface, what did I do? I considered a Gaussian surface just below the conductor, the surface of the conductor. Okay. What is the first point tell us? The net electric field was zero. Right. So when the net electric field is going to be zero here, now remember you have given some excess charge to this material. If I apply Gauss law, then accepted. So surface integral of E vector dot dA vector is equal to Q enclosed means the charge which is there within the conductor divided by epsilon naught. But what can I say about the net electric field inside? When the net electric field is zero inside, what is going to be zero on the other side? Charge enclosed is going to, sorry, epsilon naught. The charge enclosed is going to be zero. Where is it happening? It is happening in the interior of the conductor. So what is it telling us? It is clearly telling us that whatever charge you are going to give is only going to go and sit on the surface of the conductor. So this is the proof for it. Okay, if you read the statement that is given there, you will understand it. What I tried to explain. Okay. So there will be no charge inside the conductor. It should go only and sit on the surface under static condition. Fourth, electrostatic potential is constant throughout the volume. So here there are 2 points. One might confuse you, like electrostatic field is zero, whereas electrostatic potential is a non-zero value and it is always a constant. Why is it so? We'll see. So write down this point. Electrostatic potential is constant throughout the volume of the conductor. Electrostatic potential is constant throughout the volume of the conductor and has the same value as inside, on its surface. So what is meaning of it? Has the same value as inside, or you can say cancel the code inside as, that makes sense. So it has the same value inside as on the surface, as on its surface. So what is the meaning of this? But there is no charge inside. But here we are trying to talk about interior. So for interior, how are you able to define the potential? Right. So the logic is very simple. What is the relation between electric field and potential? E is equal to minus dV by dr or delta V by delta R. Okay. See, delta V by delta R, you write it for average value. dV by dr, you write it for instantaneous value. Okay. So when net electric field is zero, then this will be equal to minus dV by dr, right? So derivative of something is 0, then what should that something be? Then V should be a constant. That is the reason why they say potential is constant within the conductor. So the next question is, what is going to be its value? Its value inside the conductor will exactly be the same as that is present on the surface of the conductor. Okay, you don't have an application of it, but there is a point that you need to know. So E is equal to minus dV by dr. The net electric field is 0. So minus dV by dr will be 0. Hence, V is a constant.
So this constant value will be same at surface
As well as inside. So whatever value is present on the surface, the same value will be inside also. That is the meaning of it. Fifth one. Electric field, if you calculate it at the surface of a charged conductor, okay, that value is also constant. And how much is the value? Sigma by epsilon naught times, you have that n cap. N is generally a symbol that is used for normal, and cap is obviously unit vector. Are you able to understand? So this is what happens. Right on the next point. Electric field at the surface of a charged conductor is sigma divided by epsilon naught. Okay. Now we are going to connect all the dots. So what is the first point? Tell us electric field inside is 0. Okay, accepted. Second point, electric field at the surface of a conductor is always normal. That is the reason why they could confidently write that n cap. Accepted. Right. Third point, what did they say? Whatever excess charge you are going to give is going to reside only on the surface of the conductor. And what did the fourth point tell us? Electrostatic potential inside a conductor is always a constant, and its magnitude is equal to the value on the surface of the conductor. Okay. Having all these points connected, now let's try to derive how the sigma by epsilon naught has actually come. Okay. If I take the conductor from the third point, I know that all the charge is going to be on the surface. So I'll be considering a Gaussian surface in such a way. See, if I take a conductor like this in a two-dimensional view, if you consider Gaussian shape, it is a cylinder. You can consider any random shape you want. You can take a cuboid also. Okay. For time being, let's say you're taking a cylinder, and the electric field through that cylinder is going to be perpendicular to it. Accepted. Why? Because what does the second point tell us? Electric field is always normal to the surface. You have considered the cylinder also perpendicular to the surface only. Right? It is going to be normal. And remember, the cylinder is chosen in such a way that half of its length is above the surface and half of its length is below the surface. Okay. So where will the charge be present? The charge will be present in this region. Accepted. Right. How much is going to be the value of charge that is present in that region? Further, if I take the cross-sectional area of this conductor to flux that is coming out of this Gaussian surface through the flat surface, in fact. So it is electric field multiplied with area. What does flux tell us? EA cos theta. Here you know that electric field and aerial vector both are in same direction. Correct? Because how do you define aerial vector? Aerial vector is perpendicular to the surface in outward direction. Correct? EA into cos of how much value? 0 degree. That is why I directly wrote it as EA. But what does Gauss law tell us? You are calculating the flux. Equate that flux to 1 by epsilon naught times the charge enclosed by the Gaussian surface. What is the charge enclosed by it? If I take the surface charge density, why am I taking surface charge density? Even if you consider a three-dimensional shape, where is the charge sitting? Only on the surface. So I need to consider surface charge density multiplied with the same area of cross section. If I do that, then this satisfies the condition for Gauss law. I repeat it again, listen. So what does Gauss law tell us? Total flux through any closed surface is equal to 1 by epsilon naught times the charge enclosed by that surface accepted. So that is the theory. I hope everybody would have understood. So what I'm doing here is I'm not taking the surface integral, all those things. I directly wrote it as E into A because I'm sure about the direction of electric field. I'm sure about the direction of aerial vector as well. So I went with the basic definition of flux. E into A into cos 0 is equal to 1 by epsilon naught. Now my job is to calculate the total charge. How did I calculate the charge? Charge is basically what? Surface charge density multiplied with the area of cross section. So when I do that, sigma into, it's not area of cross section, it is any area which you're taking. So sigma into A, then A and A are going to get cancelled. What is it you're left out with? E is equal to sigma by epsilon naught in terms of magnitude. If I have to give a direction to it, sigma by epsilon naught times n cap. That's which one? 1 by epsilon naught times the charge enclosed. Are you clear with the charge enclosed? So what is the charge enclosed here? Okay, good. So only difference is I used A in your textbook, they use delta S. That's it. Yeah, sigma is dq by t or q by A, whatever you call it. Because it is uniform, right? You understood what is the meaning of uniform? Both are same. Both are same. Okay. So the only point that you need to make a note here is you ask the question, right, whether it is same for positive and negative charge. It is the same. Only thing is, in this case, you have considered positive charge. That is why the electric field is an outward direction. So n cap is outward. If the charge had been negative, then n cap would have been in downward direction. That is only difference. So that's what they have given here. See, including the fact that electric field is normal to the surface. Including the fact that electric field is normal to the surface, we get vector relation 2.35. Where is it? Where is 2.35? That is the topic. E is equal to sigma by epsilon naught n cap, which is true for both sides of sigma. If sigma greater than 0, electric field is normal to the surface outward. If sigma is less than 0, it is normal to the surface inward. That's it. Clear?
So if it's a negative charge, then electric field will be downward, right? So then the area vector will be outward. Then it will be cos 1A.
Let it be. That is not our concern.
It's negative.
Let it be. That's not because you right hand side also you have negative. No? Minus sigma into A is what you're going to write. That minus and this
So
minus.
charge
Flux is equated to 1 by epsilon naught times the total charge. Recollect Gauss law. What does Gauss law tell you? You can have a look at your notes. Charge enclosed. The charge enclosed is only in this area. Only in the region where the Gaussian surface is present. That is what I'm trying to say. Got it? And the last concept is called as electrostatic shielding. Okay, this point, let me read out. So if you consider a conductor with cavity, what is the meaning of it? So within a conductor, there is some hollow space. That's the meaning of cavity, right? With no charges inside the cavity, then what are they trying to say is, a remarkable result is that the electric field inside the cavity is zero, obviously, because there is no charge, right? So whatever be the size and shape of the cavity, so that's what they have given at the bottom. So if you take a conductor like this, one point, from the first point, I know that the electrostatic field is zero. They have given it here, E is equal to 0. Right? Electrostatic field is 0. What about the potential? It is a constant value. And the constant is equal to the value on the surface. Now, when you take this cavity, right, this cavity does not have any charge. So, irrespective of the size of the cavity, you can confidently say that the electric field inside is 0. Okay, look at the name, electrostatic shielding. What is shielding? Protection. So, something is protecting from electrostatics. Right? I'll come to that point. Be the size and so whatever be the size and shape of the cavity, and whatever be the charge on the conductor and the external fields in which it might be placed. So we have proved in a simple case of this result already. The electric field inside a charged spherical shell is 0. Do you remember this? Why is it so? Because electric field inside a charged spherical shell, the last concept of first chapter. Because there will be no charge. I told you, right? There is no mass. So there is no charge. and hence it will go and reside on the surface, right? Is zero. The electric field is zero. So the proof of this result for the shell makes use of the spherical symmetry of this shell. So listen. But the vanishing of electric field in the charge-free cavity of the conductor is, as mentioned above, a very general result. Okay, I'll come to that point. A related result is that even if the conductor is charged or charges are induced on the neutral conductor by electric field, all charges will reside only on the outer surface of the conductor with cavity. So what is the meaning of this? So in the first case, if you see, right, you took a conductor generally. So the conductor can either be charged by giving excess charge. You take that material, rub it against some surface, or you take and place it in some external electric field. That's what they're trying to say. In both the cases, what can happen? You can generate net electric field inside, but the net electric field is still going to be zero. Right? Now read the statement. If a conductor is charged or charges are induced on a neutral conductor by an external electric field, what will happen to the charges? They will reside only outside. Right? They will reside outside the conductor, irrespective of whether the conductor has a cavity or not. So to put it in simple terms, what I'm trying to say here is, if at all you take a conductor with a cavity, for example, the best example for it is car. You have a car, right? What is the outside material? Generally, all cars are made up of metals only, right? So you have those metals inside. You are able to sit, right? Can I call the place where you're sitting as a cavity inside the car? Right. So when there is lightning, right, what would happen is the charges that are getting received from the lightning, they go and reside only on the surface, and they protect you from the electrostatic effect. So that is an example of electrostatic shielding. So there will be a possibility of question like this. Let's say that there is heavy lightning that is there. Is it safe for you to sit inside a car or stand under a tree? You can sit inside a car. Because but here the context is an application of it, right? So sometimes this is also referred to as Faraday's cage. That's what they refer to. Okay, in the sense, the outside part will only take the charge, and inside the cavity it is going to be zero. And since that cavity is acting like a protective medium, we call this kind of a process as electrostatic shielding. So this point, why they have given it here, is one of the applications of it. So this is all about the electrostatics of conductor. Electrostatic potential is C. What have they given? It is still equal, it is still a constant. So within the conductor, whether you have cavity or not, electrostatic potential is always a constant. But electrostatic field and charge inside is always zero. So look at this, no? Look at this whole shape. E is 0, sigma is 0, but V is equal to V. That is the meaning of it. See, if I have to give you another example, right? You go inside a lift. Okay. Have you ever tried to speak over a phone inside lift? What happens? Will the signal be clear? No, right? Generally, if you see those, most of the lifts are made up of metals only. Right? When that is there, your phones will carry radio waves. What are radio waves? They are electromagnetic waves. They also get some electric field, right? They also have some electric field associated. So the lift which is there, outside is metal, inside it is a cavity. So the electromagnetic signals are actually shielded. They will not be able to enter the lift. That is the reason why you will not get proper signal inside lifts. So that is also another example of electrostatic shielding. Is it clear? So this is what happens. So that's why they gave the last point. The effect can be used. What can you do? This has a very important application. The effect can be used in protecting sensitive instruments from outside electrical influence. So if you want to protect any material from the electrostatic influence from outside, you can always think of this kind of a process. Okay. So I hope it is clear, right? Right. So with this, as I mentioned, the first part of the chapter is over. The next part that we need to understand is the concept of dielectrics and polarization. Okay. Shall we proceed? Yes. So any idea of what are dielectrics? What are dielectrics is? No charge. Diamonds too. Is that what you're thinking? Like something like dipole. Di is two polarities there, it is different. Here dielectric is actually an insulator. Insulator. So insulators have another name called as dielectrics. Okay. Thing is, so that's what the first point says. Dielectrics are generally non-conducting substances. Now you can ask me a question. Just now we discussed about electrostatics of conductors. Why did we immediately come to the concept of insulators? Right. So I have one important question to be asked. If you give charge to a conductor, is there a possibility that you can hold the charge on the conductor for a longer duration? I repeat the question, listen to this carefully. You are giving excess charge to a conductor. Do you think that charge is going to reside on the conductor for a longer duration? Okay. That material needs to be what? Think about it. I'm saying, I'm again taking the same aluminum sheet. You take wrap small paper out of it, okay, and you charge this aluminum sheet. That is, you are giving some excess charge which is residing on the surface. Do you think this charge will be there for a longer duration? If yes, tell me yes. If no, for that also give me a reason. How many of you think it is yes? You think it is yes? Till what point?
Since charge is conserved,
Okay. Charge is conserved under what condition? I gave you isolated condition. Now, what is going to happen? Let's think of real-time scenarios. Why would anybody charge an aluminum sheet and sit inside a cage? You're going to do in real-time world, right? Why would we sit simply? So, in a real-time scenario, world is not isolated. That is for theoretical purpose. That's a different story, right? In a real-world scenario, if I charge an aluminum sheet, can I find the charge on that sheet for a longer duration? Is what my question. Why?
Sir, because inside conductors are free electrons.
Okay, that is also there, but it has nothing to do with the free electrons. Those charges are there, right? They will get leaked to the surroundings because iron box. Okay. Okay. Okay, that is one of the points, and there's something is to do with the melting points and all those things. There, those principles are taken because electric iron works on what principle? The heating effect of electric iron. So, it's not about charge. There you're talking about electrodynamic condition, means the charges are flowing. Here I'm not talking about electrodynamic condition. I'm charging a material and I'm keeping it on my table. Will I be able to find it after some time is what my question. Okay. So have you ever observed something like this? Let's say some person is working on mobile phone. Let's say they're playing game for longer duration. Without your knowledge, you want to surprise them. Suddenly you go from back and try to touch them. Sometimes you will be hit with a shock. Has anyone experienced? Like one sound will come. Have you ever experienced it? Yes or no? No. Next time when you experience it, tell me. Okay, that is also most people say it is static. Shock now literally you not fly away. Huh? Yes, you will feel some spark coming and hitting you. Okay, so that is also a static condition. Why is it happening? Is because the charge is getting stored on that particular person. So the person himself is getting charged. We are good conductors of electricity, right? We hold those charges. So as soon as someone is trying to touch us, the charge is getting transferred from you to another. If you've experienced it, well and good. If not, it will flow. If I wear slippers and sit, it will not flow. Sometimes it has happened with me. I sit on sofa many times. I keep playing games. One kid will touch me. This happens. It happened thrice or 4 times last year. Right. So that is called a static condition. That is why is it happening? Is because you're playing with that mobile phone, right? Generally, you're using touch devices. I know I'm deviating from the topic just to give you a context of what is exactly, why exactly we need dielectrics. I'm trying to explain it. Because you people are using mobile phones. Can you tell me how is that mobile phone able to sense what you're trying to say? See, let's say there is a particular app in your mobile phone. You have it, one person will have it at one particular location. Let's say this is the screen of a mobile phone. Let's say I'm giving two Samsung phones to two people. One person will like the app here. One person will like the app to be here. It's their choice, right? There is no restriction. But how is the mobile able to know wherever you touch, it is opening the right app? It has nothing to do with locations, right? Sensor is right. Sensor is the back-end process that is running. So that is a code that is running. But even before that code is running, you are giving some signal to it through a touch, right? What exactly is happening? Transfer of charge. So your body has some charge, right? Your fingers are going to have some charge. When you transfer it to that mobile phone, it is going to give the signal to the microprocessors. Hence, that code is working. Correct? So is there a transfer of charge taking place? Right? You're a good conductor of electricity. You're giving it, and inside dielectrics are present. Moreover, any idea about what kind of sensing we are using these days? Have you ever? I'm not sure you guys would have seen. Have you ever seen mobiles where there are stylus present? You know what is stylus? I'm not talking about the Samsung Galaxy ones. The stylus where you have to literally hit on the screen to generate it. Have you ever seen that kind? Nokia used to have it. Okay. So those kind of devices are called as resistive sensing. Means they use a concept of resistance. Any idea about what the current mobile phones use? Name of your chapter. Capacitive sensing. They use capacitive sensing. That is the reason why things are very smooth. Had you used those mobiles, right, you would have literally died. Like it's like you're hitting some brick or something. It will be that hard. Sense half of the time, and you can see LCD screens where liquid you can see moving inside. LCD idea, liquid crystal display. You can see that liquid moving inside. Nowadays they are using LEDs and capacitive sensing. Why I'm telling all these things is because the concepts that you're learning is applicable in whatever device you're using in today's world. I'm able to write it here. You're able to see it there. How is it able to do? What is there at the tip of this? Charge rate. See if I can show it, open and show it. Because what is there inside? Okay. And this tip is acting as a conducting medium. Clear? Now coming back to the question. How many of you think that your conductors can hold charge? According to me, answer is no. Because conductors will start leaking the charges to the surroundings. Right? If that is going to be the scenario, we have learned electrostatics of conductors. Though they have their own advantages, there are certain disadvantages also in real-time applications. So had there not been any insulators present in this world, you cannot use your mobile phone today. You cannot use it. It is because of the presence of dielectrics only you are able to work on something of that sort. On a device called as touch screens, especially capacitive touch screens, right? So even before we know what exactly a capacitor is, we need to understand what is dielectric and what exactly happens inside a dielectric when you try to place it in the presence of an external electric field. Shall we get started with that? Right. Now the question is, electrostatics of dielectrics is what I would say. Now think of this concept. If there is a dielectric, for example, your paper is there, right? The paper on which you are writing is a dielectric actually. Okay. So if you try to give charge to that paper, do you think it is going to exist for a longer duration? Will it exist? Compared to a conductor, I'll give you same area and same length of an aluminum sheet and same length and same area of same specifications of paper in both your hands. You give same amount of charge to both the materials. Do you think both will be able to hold the charge for same duration? If no, which one will be able to hold for a longer duration? Paper will be able to hold it because what is paper? It is an insulator. So what will it do? It will not conduct the charges to the surroundings easily. It will try to hold itself. It will try to hold the charge within itself. In charge. Do the same thing. Take a paper and put it in the presence of electric field. Always take your paper and connect it to a battery. It will start getting charged. But it's that easy. Thing is, you cannot see, but it gets charged. Okay. Right, now we are going to discuss about the dielectrics and polarization. Listen, we discussed one important point. When I asked you about conductor and what is present inside a conductor, what did you people tell me? You had free electrons, right, which can move. In a similar way, if you take a dielectric, do you think you're going to have free electrons? Sorry? Here, there is no concept of free electrons at all. Rather, you will have small dipoles present inside. What will you have? Dipoles. You learned about those dipoles. No? Dipoles, the electric field due to a dipole along axial and equatorial point. Those dipoles will be present in such a way that they will be in random orientation like this initially. That is, even before you place it in the presence of an electric field. Are you guys able to understand? As soon as you place it in the presence of an electric field, what will happen? So we know this concept. Dipole placed in external electric field starts experiencing torque, and due to the torque, it is going to revolve. So they will start revolving in such a way that they will align themselves in this kind of a path. So I know that left-hand side is positive and right-hand side is negative. So the dipoles will get aligned in this way. Accepted? Like this, the whole process will, the stack of dipoles will be present. Right? Now, if you take the conductor and insulator as a difference, in conductor you only had free electrons, and those free electrons got drifted to the left end, due to which there was some space left inside the conductor, where the electric field could get pierced easily from one end to another within the conductor. Whereas in this case, if I take the total charge in the box that I've drawn, what is going to be the total charge, guys? So equal amount of positive, negative, positive, negative. So the total charge in the box that I've drawn is 0, but I can say that the ends of this dielectric has excess amount of negative charge on the left and excess amount of positive charge on the right, due to which there will still be a value of induced electric field. But here the question is this value of induced electric field going to be exactly equal to the external electric field, like how it took place in the case of conductors? What do you think is the answer? They will not be the same. Which one will be less? Obviously, induced will be slightly lesser, because there is a kind of resistance offered by the charges which are present in the regions. Okay. In such a way, if you try to calculate the net electric field in this scenario, this is going to be E0 minus E induced, and this E0 minus E induced is mathematically going to be equal to a value called as E0 divided by a parameter called as kappa. You learn about this in this kappa is different from the one you learn in electrochemistry. There also you will see some kappa. Okay. So kappa is a Greek letter. So it is defined as E0 divided by this kappa, where this kappa is called as dielectric constant or relative permittivity. It's called as dielectric constant or relative permittivity. Have this in your mind. Okay. So please make a note of this. Because of the blockage, this cannot freely flow through the other charges. It has to overcome the other charges. Dielectric constant, kappa. So it is like this. Let's see. Write like K and turn it at the bottom. Okay. So some books refer to it as epsilon R also. Epsilon R stands for relative permittivity. Both are same. Dielectric constant or relative permittivity both mean same. Yeah, please tell me.
So you're considering that the charges are from dipoles, and how will you find the internal electric field?
It is not internal, no? It is induced. So induced electric field, I'm trying to say that excess amount of negative charge is concentrated here. I'm taking only the end charges. Due to these end charges, what I can say is there is an induced electric field. Okay. So I'm only concentrating on the charges which are residing near the surface of the internal surface of the conductor. That is what I meant.
Okay.
Yeah. Right. So now we need to give the definition of what is epsilon r. So generally relative in physics means what? It is either ratio or difference. Okay. In this context, relative permittivity is defined as the ratio. The ratio of whom? So it is a ratio of permittivity of a given medium, which I will call it as epsilon, divided by the permittivity of known constant, that is epsilon naught. So generally, when you're trying to define something, right, you should always compare it with a known value. So known value will mostly be in the denominator, mostly. So epsilon divided by epsilon naught. This is what is called as relative permittivity. And what is going to be the unit for it? No unit, because it's no units and no dimensions. Is that clear? So this is what happens. And remember the value that E naught by K. I'll be using it in capacitors. So remember that value. Okay. Shall we move on to the next one? Okay. See, they have given some story. You can read it later. The next is I'll give you an introduction of what are capacitors and what is capacitance. Okay. So if you see what is a capacitor, we discussed the beginning itself. One thing, one side you have charges being created. The next is you create charge, but where will you store it? You need a material or a medium to store those charges, right? Those materials which can hold charges are basically called as capacitors, and they have a particular capacity associated with it. For example, if you take a water bottle, that water bottle has a specific capacity, right? You cannot go and fill 1 liter water into a 500 ml water bottle. So in a similar way, capacitor will also have a particular capacity, and that is what is called as capacitance, right? Now, first is how exactly a capacitor is formed in the first place. That's what we need to understand. So if you take two conductors, what are you going to do? You're going to take two conductors. The conductors can be of any shape. That's a different story. If you take two conductors of equal and opposite charges, which are separated by a dielectric medium, is what we call it as a capacitor. I repeated, two conductors separated by a dielectric medium between them is what is called as a capacitor. That's the simplest definition possible. Please make a note of it. So it is given here, see, under this 2.24, a system of two conductors separated by an insulator forms a capacitor. System of two conductors separated by an insulator is called capacitor. Okay. So depending on what kind of conductor shapes you are using, the capacitors are basically classified into three types. One is called parallel plate capacitor, and the second is called cylindrical capacitor, and the third is called spherical capacitor. The name itself is suggesting this. When I say parallel plate capacitor, how are the two conductors? Parallel plates. So parallel plate, if you have to recollect in Gauss law second application, that infinite plane sheet. Okay. Secondly, you talk about cylindrical conductor. Sorry, cylindrical capacitor. What is it? Condenser. So generally, the other name for capacitor is condenser only. Okay. What is it? You have two cylinders coaxial to each other. Similarly, what do you mean by spherical capacitor? You have two spherical shells which are concentric. Then you call that as a spherical capacitor. So one last concept is when you take two conductors and connect them across a potential source. Okay, when you connect them across a potential source, what will happen to them? Charges will get stored on top of those conductors. So Q, can I say the amount of charge that is getting deposited on the conductors is directly proportional to the amount of potential difference you apply? You're going to connect 5 volt, more amount of charge will go inside. So it keeps increasing in a proportional way. So Q will be equal to how much? So if you remove the proportionality symbol, the constant that I'm going to introduce here is what is called as C multiplied with V. So what I'm trying to say is the charge that is getting stored on capacitor is equal to capacitance multiplied with the potential difference that you apply. So from this I can say capacitance is equal to Q divided by V. Okay. This is all about the introduction of capacitors, right? They must be. It is something similar to dipole, but the only fact is in dipole the distance of separation is small. Here you need an insulator in between. So C is equal to Q by V, right? But they are not connected to each other. You give charges to the conductor, but who is holding the charges? That is why I asked you one question in the beginning. Will conductors be able to hold charge? No, they can't. Then you can ask me a question, why are we using a dielectric in a capacitor? Only to hold charge. And remember, capacitor is not a conducting device because its resistance to conductivity is infinite. Why is it so? Alternating current will give you the answer. So remember, it will not allow direct current to flow through. Capacitors block direct current. They only allow alternating currents to flow. Okay. So this is all about the introduction to capacitors. About this, we'll deal tomorrow, and maximum I think 2 more classes will be done. Okay. So regarding the test for the first chapter, right? I'll be done with second chapter maybe by Monday. Okay. So next Wednesday, we will have test in first. Okay. Start preparing. That's it. If you have any doubts, you can reach out to me. Monday chapter will be completed. Tuesday I will do some problems. Wednesday you will have test. Instead of regular class, you will have test on Wednesday in the first chapter. Okay, not in the second chapter, first. It's a subjective test. It is not according to the new pattern on all those things. I'll give for 35 marks where I'll give you MCQs and I'll give you some problems and case study based questions also. It will be a mixture because I don't know what are the new pattern they're going to give. So we'll go with the, I'll go with the assumption. Okay. So is it clear? Yes. So that's it from my side. We'll discuss the remaining parts tomorrow. One minute, no? 1 minute. Guys, those who are online, any doubts? Those who are online, any doubts? Okay. We can wind up.